probability, which falls, I guess, into the topic of statistics. Actually, it's part of statistics. So some definitions to start off with. What is probability? Yeah, simply the chance of something happening. Experimental probability, also known as relative frequency. Now that's when your probability is based upon some data that you have collected. So, for example, if we were to toss 5 coins, they land head, head, tails, tails, and heads, then our experimental probability for the tossing a head would be 3 and 5. That's what we would conclude from that collection of data. The theoretical probability is, of course, a half. It's very rare that the experimental probability and the theoretical probability will be the same every single time. At some point, they might be the same. And in fact, what should happen is if you repeat it enough times, so as the number of times you do it approaches infinity, then they should definitely be getting closer and closer to always being equal. So as the number of times you repeat an event approaches infinity, then experimental probability will approach the actual theoretical probability. Sample space, all the possible outcomes that you could get. Event space is just the number of ways for the particular event you're interested in looking at. Equally likely, as the name suggests, events that have an equal chance of happening. Mutually exclusive. Only one possible outcome can occur at a time. So an example of that, again, we'll go to tossing a coin. You can have a head or a tail, but you can't get both when you toss one coin. Bit hard. Non-mutually exclusive events is when it is possible to have more than one outcome at the same time. So for example, if we're interested about numbers, it would be possible for a number to be both even and a multiple of 3. They're 2 different events that could occur at the same time. That's the notation we use for probability. So P for probability, and then inside parentheses, whatever the event is that we're investigating. So when you're answering a probability question, don't just write a fraction down. Again, remember your solutions are not for you, it's for the benefit of someone else. So the fraction by itself is meaningless. You need to describe what is this fraction. Oh, it's the probability of heads or whatever. The probability of something not happening, we usually put a bar over the event to indicate it's the complementary event. All right, some theory for probability. All probabilities will fall between 0 and 1. So if you're going to answer for a probability that's bigger than 1, you know you've done something wrong. Got to be between 0 and 1. If it is equal to 0, then that would be something that is impossible, something that could never happen, such as, oh, I don't know, I try and start doing theory and someone talks. No, that wouldn't be probability of 0, that would be probability of 1. A certain event, it must happen. Okay, and obviously every other event falls in between those 2 extremes. If all the events are equally likely, the sample space is what we call uniform. It's a nice even distribution of events. Well, technically that's the formula. We don't usually use it because it's very intuitive probability, but that is the actual formula, I guess. The probability of the event happening. Now what do these symbols mean? So what looks like I'm saying absolute value of E means the number of times the event would occur over the number of times of all the possibilities. So the size of the event space over the size of the sample space. The complementary event little formula comes in very useful. Probability of something not happening must be 1 minus probability of something happening, because often it's easier to find the complementary event than find the actual event you're investigating, and then you just subtract it from 1 and you've got your answer. Different ways of listing our sample spaces. So when you've got an experiment, multi-stage, as I said here, simply writing down all the outcomes sometimes is the easiest way to solve the problem. So you write it down and then you simply count how many ever you want. Creating a list, so just writing them all down. 2004 HSC. So we've got this game, involves rolling 2 dice. The faces on this dice are labelled 1, 2, 3, 4 and 5 and 0. The score for each turn is calculated by multiplying the 2 numbers on the uppermost, I guess the easier way of saying that, multiply the 2 numbers that are showing when you roll them. So I'll just write out the whole sample space. They're all the different possibilities I could get. So part I of the question now becomes quite easy. Find the probability of scoring 0. Okay, how many of those end up at 0? There's one, oh, another one, yep, that one too. Oh look, there's another, and another, oh look. So we know how many we've got. 11 out of 36, there's our probability. Part 2, probability of scoring 16 or more. Wow, 16 or more. Well, there's 16, 20 is more than 16, so it's 25. 4 out of 36, which of course simplifies down to be a 1 in 9 chance. A dot diagram. Got to be honest, I don't think I've ever used one. But it's another way of listing a sample space. So a pair of dice are thrown. What's the probability? They total 3, they total 7. So a dot diagram is something like this, where you put the outcomes for one event down one side and the other event along the other side, and then you put a dot for all the possibilities. So we want total 3. Those two would total 3. So 2 out of 36, 1 in 18. Total 7, which of course is the most common outcome. And we get 6 out of 36, 1 in 6. What's the probability of totaling at least 3? Well, this is one where the complementary idea is going to be better. Because rather than working out at least 3, so that'll be 3, 4, 5, 6, rather than working out all those, it's going to be a lot easier to work out 1 or 2. And in fact, 1 would be impossible. So really it's just 2, and there's only one way we could do it. That's if we roll a 1 and a 1. So 1 minus 1 on 36, 35 on 36. Tree diagrams, probably the most common way that we've seen. But these are really good when they're not equally likely, because I could get a question like this. We've got a raffle, 30 tickets are sold, they're 2 prizes. Probability someone buying 5 tickets wins exactly 1 prize. So we're all right. Well, first prize is drawn out. They could either win or they could lose. Probability is going to be different, of course. They've only got 5 tickets. So 5 in 30 chance of winning, 25 in 30 chance of losing. But then they pull out second prize. Well, if they won on the first one, then the chance of now winning will only be 4 in 29, because they've already had 1 ticket pulled out and there's 29 tickets left. Losing 25 on 29. But if they lost on the first go around, then they had a probability of 5 on 29 of winning and 24 on 29. Each branch of your tree diagram, all the probabilities should add up to 1, because you should have all the possible outcomes there. And then how do we work it out? Well, we multiply along the branches. So we can work out win-win, win-loss, loss-win, or loss-loss. Multiply along. There's all our probabilities. Probably more work than I needed to do to answer this question in reality, because we just want to know exactly 1 prize. Well, that would be win-loss or loss-win. 25 on 87. Now, if you're unsure whether to add or multiply, speak naturally. If you feel yourself saying the word or, you're adding. If you feel yourself saying the word and, you're multiplying. What's the probability of winning at least 1 prize? So again, I'll use the complementary idea. What's the probability of not winning at all? So loss is 20 on 29. So 1 minus that would be 9 on 29. Okay, there's a bit of a recap of our basic probability.